So I'd like to welcome our speaker this morning, who is Wayne Goodman. Wayne received his bachelor's degree in geology from Ashland College and his master's degree in geology from the University of Cincinnati, which is where I met Wayne. And I'd like to point out that HASP has enjoyed a rather robust connection with UC geology because, of course, he's here presenting today. I did a class in July. We have Ed Hansen scheduled for a climate change class next term. He also did time at Cincinnati. And Bill Harrison from Western Michigan University has presented HASP classes, and they are all UC geology alumni. So Wayne, after leaving Cincinnati, went to work for Shell in Houston, right?
Mm-hmm.
And then from there went to work in Tenneco in Colorado. And since then has been working for Core Energies here in Michigan, which is based in Traverse City, Michigan. And I'd also like to welcome his wife, Marty, who's in the back row. Marty's also a geologist, so this is probably the highest concentration of geologists you've had in one room in the whole history of HASP. So anyway, Wayne, welcome, and it's your microphone now.
It's time. Well, thank you, and welcome to everybody, and welcome to everybody also participating online. And yes, we're surrounding you with geologists today, and especially the smart ones. Now, she was the smart girl at Cincinnati when I was there in geology. She was an exceptional student, and when I took a training class at Shell in the 1970s, when I came there as a 20-something-year-old grunt geologist, I had to find another smart geologist, and I found her, and she actually accepted a date with me, and they didn't know what they were getting themselves into. But 47 years later, here we are, and we found our way back to Michigan some 28 years ago, and we've had a fun ride since, and we'll share a little bit about some of the stuff that I've been doing over the years. Currently, I am a consultant. I'm a standalone consultant. I do affiliate with Core Energy in Traverse City quite a bit. I've been a consultant and a partner at Core for about 20 years, and most of my consulting work is done with Core because they've kept my plate fairly full. And I'm several years past traditional retirement age. And as I was sharing with a few of you folks beforehand, I'm stubborn, so I haven't totally gone away yet. I still like to get my fingers dirty in what Core is doing and stay engaged. So that's a little bit about me. And we're going to kind of tiptoe through the energy history, especially regarding oil and gas in Michigan over the next hour or so, starting out with things that we're primarily concerned about the fossil fuel industry itself. And we'll get into how the fossil fuel industry has morphed and is morphing right now as it really needed to remain viable and relevant, and where that's all taking us. At some point, fossil fuels aren't going to be there. And all of us in this room are kind of part of that bridge between fossil fuels and whatever thing or things become next. And the time frame in which that happens is really kind of tough to define, as I'll explain. Okay, and this is kind of a tiptoe of where we're going to go in the next hour or so. I'll give you a little bit of a brief history on the Michigan energy industry. I'm using my pointer here and just walking through the slide here for those that are watching at Zoom. We'll talk a little bit about the pure geology of the Michigan Basin and its sediments, and which ones really are conducive to trapping and producing oil and gas. We'll talk a little bit then, maybe on a more big think scientific nature, and maybe a little bit of a socio-political nature about where we're going, what's going to happen after fossil fuels, how long are we going to be dependent on them, and what can we do to be better stewards of using them until we get to whatever that next step is. And hopefully I'm going to leave plenty of time for all the questions you're going to have for me. So that's kind of where we're headed in a nutshell. And key ideas, and again, for those at home, I'm just going top to bottom on this, a little bit of energy history, the economic impact of the industry here in Michigan. We'll tiptoe through a few of the more prominent oil producing zones. We'll talk primarily about carbonate rocks, and those are limestones and dolomites. In Michigan, those are our primary reservoir rocks for the most part, and that's a little bit different from what most large oil and gas provinces have to bring us. We'll talk a little bit about where the Michigan Basin sits geologically, where on what the continent of North America used to look like it's at, and how that influenced sedimentation. We'll talk a little bit about resource plays and about fracking, which is the way you get oil and gas out of resource plays in oil shales and gas shales. My niche at core does not involve those, but I have been involved with those kinds of projects over the years. And we'll talk about bridge fuels, sustainability, and we'll talk quite a bit about carbon dioxide and what I do at core as far as enhanced oil recovery using what has classically been considered industrial waste CO2 is concerned. We utilize it, we put it to work, and then we put it out of harm's way. So it's kind of a fun task that has become part of my later career. Okay, well, Linda kind of told you who I am, so I guess this is pretty repetitive actually, but my wife and I have been in Michigan on the ground since 1996. I have worked the geology of Michigan for a lion's share of my professional career, starting with Shell back in 1975. So if I'm an expert at anything, and that's always arguable, then Michigan and Michigan basin geology are probably it. I've published a handful of papers, I've given a handful of talks over the years, and more often than not, that's been the kind of project in which I've worked, although I have worked in just about every sedimentary basin in North America, at least a little bit over the years. So kind of tiptoeing through things, well, I talked about the fact that Michigan has been an oil and gas producer, maybe not one of high renown necessarily, but we've been at this here in Michigan for roughly a century right now. And again, for those at home, I'm now working my way through the bullet points on my slide here. Michigan first became an oil producer in 1925 in the Saginaw oil field located just outside, not coincidentally, the city of Saginaw. And oil production in our state peaked roughly 40 plus years ago in 1979. Natural gas production peaked about 20 years later in 1997. In both cases, that happened to a large degree by virtue of oil and gas plays fairly close to where I live up in Gaylord. There was a broad oil play made basically from Manistee over to Presque County in the 1970s, 80s, and into the 90s. And then a natural gas play evolved in very much the same area, primarily in Otsego and Montmorency counties in the 1990s and 2000s. Importantly, because we are such an industrialized state here in the Midwest, Michigan has been a very key location for the location of pipelines that move oil and gas product, not just that produced here in Michigan, but that has been produced elsewhere, all across this portion of the country. So we have a lattice work of pipelines beneath us. And in spite of what the conversation has been about Enbridge in the past few years, by and large, that has been a very safe way to transport energy. And it sure, from my opinion at least, would beat the heck out of having trucks on our interstates moving oil, compressed natural gas, et cetera. It is highly regulated. I don't get involved in that aspect of the business, but Michigan has a reputation as being one of the most highly regulated states for the safety of the oil and gas industry, including pipeline construction, pipeline maintenance, and operations, which I think is why we're having such a long conversation right now about the move to replace Line 5 up at the Straits of Mackinac. And we may get into that a little bit during our discussion time. By the way, just as a quick sidebar, if I'm talking too rapidly, you're not having a chance to drink this in. If I'm talking too fast, give me a sign to slow things down a little bit. I often talk fast because one of my hobbies, so to speak, is I call play-by-play for high school hockey. So I'm a chatterbox. And sometimes I talk fast, and I used to be a debater in high school. So once again, I'm trying to jam as much information into a short conversation at times as I possibly can. So if I'm overwhelming and not giving you a chance to digest, throw hand waves at me. Okay, Michigan oil and gas production. These are statistics that are a couple years old, but we are the 10th largest natural gas producing state and number 16 in oil today. And folks at home, I'm looking at the box in the left central part of my slide right now and highlighting that. In each case, this is a very tiny amount of the gas and oil production we have nationwide, but it is important to the economic health of our state. We have about 10,000 jobs directly involved in Michigan's oil and gas industry, and several times that in ancillary service company business and the like. So it's a pretty important economic facet in our state that we really don't talk very much about. So I'm happy to be a small part of all of that. And as I note in the bottom box here, we produce about 25% of our state's total energy production. Most of that happens through natural gas. This is a quick map look. Again, for those at home, I'll be kind of waving around with my pointer here to show the various oil and gas plays that are prominent in Michigan's history. Let's see, we'll start over here in Saginaw Field. This is the original production back in 1925. Very small in nature, but it kind of got the engine started, so to speak. Early post-World War II and for a couple of decades afterward, if you take a look at this slide, and I'm pointing now toward those northwest to southeast bands you might see in central lower Michigan, those are a number of fields that have a little bit of a fold or a closed structural setting in which the rocks of the Devonian age, which are primarily limestones and primarily patch reefs and things of that sort, were able to be found through mostly surface geology and produced a lot of oil and gas back in the 40s and 50s and really kicked the industry off. Historically, Mount Pleasant was the capital of Michigan oil and gas geology until much more recently in time. Then in the mid-1950s, this little curiosity almost in our backyard here in Calhoun, Jackson, and Hillsdale counties was discovered. That is the Albion Scipio field. That is the only giant oil field in Michigan. I'll talk about this more in depth later, but it has produced well over 100 million barrels of oil. And it was found kind of serendipitously. The story about how this thing was found is pretty cool. We'll talk about that in a little while. Getting into the late 60s and then especially the 1970s, this linear band going from Manistee County, upper left for the folks at home, to Presque Isle County, upper right, that linear band is a large number of oil and gas reefs, Silurian reefs, they're called pinnacle reefs. They grew vertically very rapidly in response to a rising sea level. And they were first found in the late 1960s when seismic data became good enough for us to actually explore fairly successfully for them. And that's really how I cut my teeth in the oil and gas industry some 45 years ago, was working on these Silurian reefs for Shell. And they've been kind of my pet now for 45 plus years. And oops, I'm going to go back. Sorry about that. Because of the pipeline and infrastructure that was associated with those reefs, 20 years later, evolved a shallow gas shale play in the Antrim Shale, the Devonian Shale that is only a few hundred feet below the surface. It's depicted here in red. A lot of production up where I live near Gaylord and over to Montmorency and Alpena counties, west over to Kalkaska, and a small bit over by Manistee as well. That was a dominant gas play in Michigan in the 1990s and for about a decade and a half forward. That's where fracking has most come into play in Michigan over the years, and that play is kind of on its ebbing stages right now. And then, whoops, I did it again. There it is. Got to find the right thing for the pointer. I talked about Albion Scipio. There have been some smaller fields of the same age, which is Ordovician, Trenton, and Black River in age, found in Calhoun County and actually over into Kalamazoo County in the past handful of years. Again, modern seismic has allowed some smaller spur fields to be found that are economically of value. Well, I mentioned the fact that we have about a century of oil and gas production in Michigan. It actually goes even further back than that. And I'll be showing for the folks at home the bullet points on the left side here. The Michigan Basin mostly comprises Michigan's Lower Peninsula as a sedimentary basin, but it also includes a fair bit of Western Ontario over towards Sarnia and over almost as far as London, Ontario. And back in 1858, before Titusville, Pennsylvania was found as our, quote, traditional start to the energy industry in the United States. This is a picture on the right of the oil museum at Oil Springs, Ontario, which is aptly named because that is where the first commercial oil was discovered and developed in North America. And it's really a part of the Michigan Basin. And some of those fields at Oil Springs are still productive today to the tune of maybe a couple of barrels a day. But it is such an historic place for the folks in Ontario that they have wells operating today that were first operated back in the mid-1800s. And all of the works of the oil and gas production, the derricks, the pipeline systems, et cetera, are made out of wood. And they've left that in place to kind of show what our roots were. And they still work today. It's a pretty cool place. I think the museum is free if it's not. It's a nominal cost place, and I'd recommend it for a weekend road trip if that sort of thing gets you interested. Michigan crude oil peaked in production in 1979. I was still working at Shell Oil at that time, and most of the oil that we produced at that time came out of those Niagaran age reefs. And when I use the term Niagaran referring to those reefs, that means that the rocks that oil is being produced out of are the same age as the rocks that form most of Niagara Falls. Every rock worldwide has a name of a formation attached to it, which relates to a place name where that rock was first described and first studied. So in the case of the rocks that are about 1 mile below where I live in Otsego County, Michigan, those rocks are called Niagaran because the type section for those rocks is over at Niagara Falls. And the rock varies a little bit in what it looks like at Niagara Falls, but it's still a carbonate rock, a limestone that has a lot of reefy material in it. In the case of those in Upper Michigan, that reef is encompassed, as we'll talk about a bit more, by bedded salts on its flank, bedded salts on its top, and non-porous rocks at its base. So that rock has trapped oil and gas in almost a perfect container, so that if one is successful in finding the container seismically, it can be produced rather efficiently. Right now, oil production is fairly flat and has been going down by 1% or 2% a year for a number of years since that 1979 peak. Natural gas, similar story. As I mentioned, the Antrim Shale produces almost every 80 acres. There is a well in this swath of red here. I'm at the slide on the lower left for those at home, showing the red splotch that goes between Kalkaska County on the west over to Alpena County on the east. At one time in the late 1990s, there were over 11,000 shallow wells producing out of that horizon. And that number is now something like 8,000 or 9,000. With time, both gas and oil wells steadily decline in production. Gas wells do so much more rapidly. So we're down maybe to, about 60% of the daily production that was true at the peak back in the late 1990s. And total gas production today, referring to the slide on the lower right with my pointer, totals about 61 billion cubic feet per annum. And that was down from something more than double that, actually about 4 times that back in the late 1990s. So oil and gas plays in Michigan comprise several different sorts of things. As I've mentioned, we have a lot of so-called conventional production where you're producing out of fairly porous, fairly permeable, in Michigan's case, mostly limestones and dolostones. Does the term dolostone or dolomite, is that familiar to you folks, or should I give you a quick explanation? Okay, limestones are calcium carbonate, and most shelly materials, animals that live in the sea, have calcium carbonate skeletons or exoskeletons. With time and under certain chemical conditions, limestone can be converted to dolomite or dolostone, in which case some of the calcium ions are replaced by magnesium ions. So you get a magnesium carbonate. When that chemical transformation happens, there is typically about an 11% increase in porosity in that crystal of dolomite. And so that opens up a more attractive reservoir rock, if you will, that sometimes can be very effective as a place to entrap and produce oil and gas. But the two kind of often work hand in hand, especially in areas near an old paleo shoreline or paleo landmass where that chemical change happened more readily. So conventional plays pretty much are traditional traps, a structural trap or a fold trap that is sealed on the top and on the flanks by less permeable rocks. A non-conventional play, sometimes called a resource play, typically on a nationwide basis, these are the fields that produce out of oil shales and gas shales. They typically require fracking. The Antrim Shale is a play that requires a small amount of fracking. We'll allude to that a little bit later on. And there are other plays in Michigan that may also become fracking style plays, one of which is a shale called the Collingwood, which has been produced to a small degree just south of the Niagaran Trend in recent years. Hasn't really been commercial. At some point it may be revisited, but it didn't do too well here, but it is very much akin to both in time and in how it was deposited to the Utica Shale, which has been a very prominent producing horizon in Ohio and western Pennsylvania in recent years. So there is a chance that at some point forward that could happen, at which time we'll probably continue to have the conversation about how to frack wells, how to do so without A, using too much fresh water, which I think is the biggest concern about fracking, and B, making sure that we're doing it in an area where fracking can be done without any kind of harm. And in fracking, all one is trying to do is one is trying to take a natural fracture in that rock and prop a fracture with 1 or 2 grains of sand to kind of open up a little envelope. If you've seen the cartoons in the Detroit Free Press that show Satan in the bowels of hell with this big frac thing going on in the world being blown up below the surface, that's really not how it works. It's quite a bit different than that. And we're also fortunate that we have a highly regulated environment to make sure it's done safely and well in our state. Okay, Michigan's oil and gas zones are all part of the Michigan Basin, which is a large sedimentary basin located on continental crust, part of today the North American plate. You've probably heard of, and maybe even talked about continental drift a little bit. Most of North America comprises one very large structural plate. It's evolved quite a bit over time. There have been moments when much of it was under salt water and was part of interior inland seaways. And that's where most of our limestones and dolostones were laid down. And again, going through the bullet points for the folks at home from top to bottom, most of our sedimentary rocks here were deposited during the Paleozoic era between 550 million and maybe 240 million years before present time. And they are mostly limestones and dolostones, and they primarily comprise rocks from 3 ages, going from oldest to youngest, the Ordovician period. That's the Albion Scipio field and the stuff that's being found over not too far from us right now in Kalamazoo and Calhoun County. That's about 470 million years ago. 50 million years after that, the reefs and the Silurian that I worked in, primarily in northern Michigan. And then the original fields around Mount Pleasant, West Branch areas in central Michigan. Those are the youngest fields. They were found first, and they date to about 385 million years before present. They were more readily findable because folks could take shallow wells, including old water wells, and kind of connect the dots with various layers of rock and be able to find very tiny, subtle structures that could be drilled deeper to look for entrapped oil and gas. And that's really how the program for the Devonian got started. So here's our little Michigan Basin in the middle of the Midwest. And this is a depiction of what really what the North American plate looked like through most of geologic time. We are part of a large platform that goes all the way up west of Hudson's Bay and into the subarctic. And this area is just latticed with a bunch of small basins that were good places to collect sediments for literally hundreds of millions of years. And Michigan is this little cereal bowl-shaped basin that comprises mostly the Lower Peninsula with a little bit of adjacent Ontario and maybe a little bit of adjacent northern Indiana as well, and even a smidge of Ohio. And it has a very similar set of roots, if you will, to the Appalachian Basin along the Appalachian Forelands to our east, the Illinois Basin to our immediate west-southwest, and then to a lesser degree, some of the other large basins in the central part of the basin, or central part of the continent, rather, Forest City Basin in the Iowa, Missouri, Nebraska area, the Williston Basin in the Dakotas. And accordingly, since the Craton is this fairly structurally quiescent area with not a lot of faulting and a fairly quiet geologic history, these are called intracratonic basins. And shallow seaways quite commonly are a big part of their theme and their history. I'm off for a water break. All righty. Back to it. And we call the Michigan Basin and its so-called cousin basins part of the Basins and Arches province. I'm looking for the folks at home at the map right now showing the Michigan Basin and its location. You can probably see the outline of the Great Lakes surrounding that little cereal bowl. And there are arches, structurally high places that kind of separate the Michigan Basin from its nature. Those on its southeast flank are most prominent, the Algonquin Arch, which goes into Ontario, the Finley Arch, which goes into west and northwest Ohio. On the west side, we are flanked by the Wisconsin Dome and a large arch that goes up into the Canadian Shield called the Fraser-Dale Arch. And This is rather typical of what most North American sedimentary basins look like and how they are formed and maintained. There is a lattice work of deep-rooted structural history that keeps these basins more or less in place and allows them to catch a tremendous amount of sediment over that long, slow, steady march of geologic time. And I think I've just basically told you about most of this. I'm going to skip that slide and move ahead a little bit. As I mentioned, we have complex structural underpinnings here. We have a lattice work of sutures, and we have Precambrian, pre-sedimentary rock terrain boundaries. That's the granite like you see up in northern Ontario when you go north of Sault Ste. Marie, the Canadian Shield. The Canadian Shield has spectacular granites, gneisses, igneous metamorphic rocks. They look pretty homogeneous at first glance, but there's a lot of complex geology there that really defines how the basins, including the one we live in, actually came into form and how they've maintained that form over the course of time. This is a slide that shows in a very quick fashion some of the rifting that takes place. Continents on a day-to-day, year-to-year, century-to-century process don't change a whole lot, but continents do break apart and re-weld with time, and we've had several instances of that in present-day Michigan. For those at home, I'm looking at the area in red on the map on the right. Those are various rifts where the continent of North American plate tried to break apart and didn't quite succeed, but it left these large rifting areas that collected sediments in them before all of the Michigan Basin cereal bowl sediments actually began to collect. And those rifts form a great deal of the structural underpinnings of the Michigan Basin as well as its adjacent basinal provinces. And you'll see on the map there also a north to south trend called the Grenville Front. The Grenville Front is a roughly north to south line over which the Precambrian granite terrains, such as those you see on the Canadian Shield, actually changed in chemical composition quite a bit. And that front itself represents an area of long-time structural weakness and or structural change. And it is one of the key things that also helped our basin and adjacent basins to evolve over time. It's pretty cool stuff. It's very complex, and we're just learning about it really in recent decades because we couldn't see this stuff seismically until fairly recently. That's kind of more of the same. I'm going to pass on that one. This is a cool slide. I'm going to talk about it very quickly. This was done by a gentleman by the name of B.V. Sanford, a Canadian geologist, who really wanted to see how continents formed, and he was able to map this lattice work of northwest to southeast and northeast to southwest structural trends across the entirety of North America. And between the intersections of these major structural fronts or zones of weakness evolved the various sedimentary basins. So you can see here that the Michigan Basin at the lower part of our slide with the red arrow for those at home is bounded by the Wisconsin Arch and Dome to the south, the Algonquin Arch to the east, and the Frontenac Arch to the north and northwest. And that's a very important reason why we have 3+ miles of sedimentary rock here in the Michigan Basin and why so many of those horizons actually had a chance to generate and entrap oil and gas. It's pretty cool stuff. It's complex. And we're getting to the point now where we know enough about that early history of the basin to get to be borderline dangerous, if you will. Okay, and I think I'm going to pass on that one and move ahead a little bit. Talk a little bit about the various productive intervals in the Michigan Basin. I've kind of alluded to them a little bit. And on the slide it's shown right now on the right-hand side, you'll see some colored text boxes for those at home. Youngest rocks are at the top, and most of the rocks that are carbonates, limestones, and dolostones are shown in mostly blues. The Traverse Formation is a Devonian formation that produces oil and gas mostly in the middle of the basin. The Dundee, another Devonian horizon, does likewise, as does its lower member, which is often called the Detroit River or Richfield Formation. Midway down the slide, you'll see the Niagaran text box, and you'll see in the color depiction there, we've drawn a little reef there. That's part of that pinnacle reef system I alluded to. And over the top of that reef, you'll see some purples. Those are anhydrites. Anhydrites are bedded gypsum that has lost its water content and provides an almost perfect impermeable barrier. So that provides our top seal to a lot of the Niagaran rocks, as does a lot of this orange stuff above it, which is bedded salt. So we've got kind of a double bang as far as top seals to the Niagaran, which makes it an almost ideal reservoir rock because stuff doesn't leak out of it. And then the Trenton Black River down below that is shown in the lower blue zone at the bottom. That is another primarily carbonate rock, although it has some shaly or muddy debris in it as well. But that is the zone that produced the Albion Scipio giant field out of a very unusual structure, and has produced some adjunct fields over in our neighborhood here from similar structural trapping. And they produced a lot of oil over the course of time. You can see that we've produced historically 110 million barrels out of the Traverse, 350 plus out of the Dundee, 100 million plus out of the Detroit River. The Niagaran as a formation is the kingpin with 525 million barrels out of over 1,200 discrete reefs. They're tiny, but they're very prolific and can be very productive. And then the Trenton Black River has produced 166 million barrels with 2/3 plus of that coming out of a single field. And just as a quick aside there, this data comes from our friend Bill Harrison, who has spoken to HASS before. Bill, like Linda, was one of my classmates back at Cincinnati, and he has been a professor at Western Michigan for about 40 years and now is the manager of the McGree Rock Facility in Kalamazoo on the Western campus, which is among the largest repositories of rock samples and other geologic data on the planet. So I rely heavily on regular dialogue with Bill and his wife, Linda, another geologist from Cincinnati, who was the business manager at McGree. More Bill Harrison stuff here. And this just kind of gives you a quick timeline. The green line shows kind of the volume of oil history or oil production history through the years. Here's that first blip during World War II we talked about out of the Devonian, Dundee, and Traverse, a lull into the 50s until Albion Scipio hit, and the Trenton Black River had a big spike. Here's the big Niagaran Reef spike that is directly related to major evolutions in the quality of seismic acquisition data and seismic interpretation. And then we ebb back off again. And then in the last 15 or so years, we've got a new blip forming now, which I think is going to grow from Trenton Black River, Albion Scipio type fields. So I think that's where a lot of our future sits with regard to oil and gas. We've kind of talked about those concepts in general. So I'm going to move on ahead and let's look at some pictures of rocks because they're more fun than having me talk all the time. So we're going to look at some core slabs. These mostly do come from the McGree Research Center in Kalamazoo. Devonian carbonate rocks typically have a lot of fossil debris in them. I'm looking at the left slide right now, and those little rounded fossils you see are two different kinds of animals. One of those is solitary corals, and the other is an animal called a bryozoan, also known colloquially as a moss animal. And those are major reef components or reef building components in much of Paleozoic time. And then we have at the top of that slide on the left, that linear, long layered light colored rock. That is called a stromatoporoid. They were an animal closely related to modern day sponges, but they had a calcium carbonate skeleton. And they actually did a lot of the reef forming during Ordovician, Devonian, and Silurian time. And when we get to the Niagaran slide, you'll see some big heads of stromatoporoids. They kind of shape themselves to the terrain they're sitting on, so to speak, but they're big reef builders. The rock on the right is more of a layered off-reef set of carbonate rocks. And these layers at the top of the slide on the right are primarily algal mat material. And then you can see a little bit of biologic debris below there with the dark spots, excuse me, being porosity that is developed primarily when this rock was dolomitized. And that's what the Devonian looked like from a paleogeographic standpoint. I've shown the North American continent and how it has been paleogeographically interpreted by a Colorado geologist by the name of Ron Blakey. In Devonian time, we were sitting in the middle of an interior seaway, mountain building going on in the Appalachians to our east, a little bit of mountain building off the Pacific coast, defining the North American plate within, which with lots of shallow incursions of salt water from the major oceans. And we were in the midst of one of those saltwater basins. There wasn't a whole lot of sea level variation during Devonian time, which means that when reefs grew, they tended to grow laterally and rather slowly in patch reefs that didn't have an awful lot of relief and are fairly simple looking. So there were no dramatic 500, 600, 700 feet piles of carbonate rock. They were packages of rock in the thickness of 10, 20, 30 feet. And if those rocks were gently folded after being deposited, they offered a chance to entrap decent volumes of hydrocarbons. The Dundee Formation was open marine in the eastern side of present-day Michigan. There was a lagoon, kind of like the offshore Gulf Coast lagoons to the west, with a linear north to south series of patch reefs and shell banks in between. And that's where most of the oil and gas was entrapped. It was in these shelly banks. Here's a couple looks at some Dundee rocks. And again, you see the, oops, I did it again. Go back. Got to work on that pointer key a little bit. Once again, bryozoans and corals. The dark material has a lot of organic debris in it. And quite typically, if that dark debris is deposited and then trapped in a non-oxidized environment, that's where your oil is being generated, is from all that organic debris that never really got rotted out shortly after deposition. Oil and gas don't come from fossil dinosaurs. I know that's kind of a neat colloquial thing that we talk about, and you might hear the guys in the newspapers talk about that we're producing our gasoline from fossil dinosaurs. No, doesn't work that way. It works from shallow marine deposits that were preserved in an anoxic environment so that all that organic sludge, if you will, under high temperature and high pressure can be cooked and eventually can generate and expel various kinds of hydrocarbons. Some additional Dundee rock examples. These are shoaly type rocks in both cases. All kinds of tiny fossil debris in here. This was worked by longshore drift and made what in essence is a sandstone composed of calcium carbonate pieces of dead animals. And here we've got more Dundee type examples. Once again, on the left, we see this layered kind of algal mat material. Algae are a big part of what was left behind in the carbonate regime and environment. And on the right, we've got a lot of tidal flat rock here with little pinpoint blebs of porosity in it. This is typically what you would see if you went to a limestone beach in the Gulf Coast today, lithified that stuff, and then let it kind of sit and preserve over millennia. You get these fine pinpoint blebs of porosity in here, and that's where the oil and gas gets to move and flow. This is more anhydritic. So again, this is basically bedded gypsum on the lower left core rock here, taken out of Isabella County near Clare. And once again, a lot of layered laminated rock here, which indicates a very low depositional energy deposit and probably something fairly close to a landmass. This might look a lot like what much of the shoreline of the Persian Gulf looks like today, very similar type of environment. This is the Albion Scipio type rock, and these are all dolomites, and they're very unusual dolomites. I won't call them unique, but they're close. And what has happened here is that these dolomites were formed, and that's the white stuff here on all these slides. These were formed when fluids with a lot of magnesium in them from the upper part of the Earth's crust came up from below at very high temperatures and pressures and very quickly converted selectively portions of limestone into what is called high temperature dolomite, sometimes called zebra dolomite, sometimes called HTD dolomite, standing for high temperature dolomite. And dolomites produced in this fashion by that high temperature inclusion of fluids. This is a what's called a petrograph here. This is a thin section of that dolomite crystal. And when you put light on these crystals under a petrographic microscope, most dolomite crystals go extinct at a very certain point as you run light across that surface. High temperature dolomites do so, but they kind of move slowly from left to right or right to left instead of being one wham bam stoppage of light moving through the crystal. And so they have very distinct characters, whether you look at a thin section or look at the rock itself. And they usually happen, here's a case, this is vertical cross section along a fracture or fault, fluids moving up from the upper mantle, lower crust, and dolomitizing along that fault boundary or fracture boundary as they go. So Trenton Black River fields that are found in this fashion can be just a couple hundred feet across, but can be 30, 40 miles long. And if I were to walk from where I'm standing right now, and if I'm in the middle of one of those high temperature dolomite fields, and I walk over to about here, 10 feet away, there is no evidence if I take a core out of this rock that I'm 10 feet away from high temperature dolomites. The demarcation line is that sharp, so it takes amazingly accurate seismic data to look for the little bit of a downdrop fault block like that one right there, which might be just a few feet in nature, but that's where these traps live. They're tough to find. And talked about that. Here's a cross section once again of one of those Ordovician structures. They're colloquially called flower structures, and this is an interpretation that my geophysicist partner at Core did of one of those fields, and you can see it is very heavily fractured. These layers of rock are displaced in big time fashion. We've talked about those details, and those I'm going to jump ahead a little bit. And there's another shot of the zebra fabric, these white and off-white colors in dolomite that reflect that high temperature dolomitizing fluid. And commonly, they happen to be located along areas where that sediment has been dewatered and left an easier conduit for those high temperature fluids to move. And as I mentioned, new technology in seismic has allowed a lot of new fields to be found. In the 1990s, several were found over in Western Ontario and adjacent Michigan, I think over in Washtenaw County. A couple of fields were found over there. In the last 10 years, it's been right over here in Southwest Michigan. Calhoun, Kalamazoo counties have been kind of a hotbed of activity of late. Several nice sized commercially successful fields have been found, but no big whoppers like Albie and Scipio, at least yet. And a quick look at the pinnacle reefs, because I know I'm not managing my time too well. These are big stromatoporoids that form a large part of those big vertical reefs I talked about that can be 500 to 600 feet tall because sea level was rising so rapidly during Silurian time that the reefs were going vertically instead of laterally to kind of keep up the pace as sea levels changed. Sea levels change for a lot of reasons that mostly have nothing to do with human activity, and they have done so throughout geologic time. We're just getting now to the point where we can measure the rapidity of sea level changes more effectively. We're still kind of young on the learning curve for that, but these Silurian reefs were building during a time when they had to build and build rapidly vertically just to maintain being alive. And we explore for those sizably. Once again, we had a major intracratonic seaway here in Michigan. There was one that looked about the same over in the Appalachian Basin at this time. For those at home, I'm looking at the slide on the right and those blue areas of seaways in the center of the North American continent. There are big reefs that grew vertically in the Appalachian Basin, very much akin to those that I've explored for over the years here in Michigan. This all took place about 420 million years ago, and the evolution of good modern seismic and the ability to filter it effectively in the 1960s allowed us to explore for those things really effectively for the first time. When I was working at Shell had known for 15 or 20 years that there was a high likelihood that big reefs existed in northern Michigan. They just didn't know how to find them. And I kind of got in at the early end of that. And so I got to go to school on a lot of really vanguard pioneer researchers that helped take me to school on how to get smarter. And that play, as I mentioned before, comprises over 1,000 reefs total, is produced, including both the northern trend and a smaller southern trend that runs across from Kalamazoo County to Metro Detroit. Collectively, they have produced over 500 million barrels of oil, well over 2 trillion cubic feet of gas. And today, those same reefs are also used, by the way, for natural gas storage. Abandoned reefs make great places to store natural gas. So the pipeline companies store natural gas in these things during the saddle season when we're building up reserves to get through winter. And then we can move those through pipelines so that we can provide natural gas to both Michigan and the Midwest during the cold weather months. Michigan is the #1 state for gas storage. It's a little known part of our energy history here. We're going to jump over a couple more of these. Let's see, my magic moment is 1050, is that right? 1050 is when we turn into pumpkins? Okay. So I'll try and move ahead here so we can cover, at least to some level, all the myriad of topics I wanted to discuss. But here is a depiction of what the Niagaran Sea looked like when those reefs were deposited. The pinnacle reefs were deposited on a ramp well off the shore of the then saline basin here in Michigan. There was a large carbonate bank or platform further landward from these reefs, and that was a very, very thick mass of carbonate rock, hundreds of feet thick, for the most part, very low porosity and permeability, and also no bedded salts up here to trap anything. So it's beautiful looking rock. At first glance, you think, boy, that would make a great oil or gas reservoir, but it doesn't because there's no way to trap the hydrocarbons. Our edges of our bedded salts that happened after reef deposition time is right around here and right on top of those pinnacle reefs. And we have several hundred feet of bedded salts in late Silurian time that enveloped both laterally and on the top those reefs and provided an absolutely perfect seal for them. There's a cross-sectional depiction of that once again. Here are our reef packages of rock here. The greens are bedded salts, which pinch out as we go to the north in northern Michigan up toward the straits. The purples are bedded anhydrites that often drape over the top of the reefs and provide a secondary seal. And again, here's what a stromatoporoid looks like. This is a big domal one. Some of these things were literally as big as a house, just huge, huge mounds of big spongy-like material that had calcium carbonate skeletons in them. Neat stuff, fun to play in. And seismically, here's kind of how the challenge went. This is a series of maps for the folks at home. The map on the right is a surface map from Oceana County, and all of those lines across there are two-dimensional seismic lines that were acquired over this area in the 1960s into the 1970s, and maybe even a little after that. And that big reef right there was missed, or at least not defined by any of that lattice work of data. We just didn't have good enough quality data to make that work. And the slide on the left is a cross-section of one of those old two-dimensional lines. And you can kind of see some little things happening at about the middle of the slide where I've got the red box there on that left slide for those at home. But you really wouldn't be able to say, gee, there's a 500-foot tall reef sitting out in the middle of that someplace. Well, here you can see it in the center slide because these two dark events, which my partner Alan has depicted here with a little bit of a color highlighting in yellow, this is a major event that defines the intersection between a thick bedded salt and a bedded carbonate. And once that line of demarcation disappears, there's your reef because it's all carbonate. So there's no velocity contrast in that center cross section there to define where the salts are. And the same thing is happening to a lesser degree in this lower event that happens at about 740 milliseconds, if you're following along with us at home. Again, you see a little bit of a change in character, and that change in character is once again because we've lost that bedded salt layer. So as one of my longtime geophysical partners told me, in Michigan, the key is when you see something, in other words, you see these layer cakes, something means nothing. It means you've got nothing to go for. When you see nothing, you've got something. And that's kind of a maxim that we lived by for a number of years. And that really all happened in recent years because three-dimensional seismic, which allows you to do a very narrowly spaced series of shots in one direction and a narrowly spaced set of receivers in the 90-degree direction to that, gives you very narrowly defined bins, which can give you a much more crisply defined depiction of what the subsurface looks like a half mile or more below. And this is one of my partner Alan's pieces of software that is really cool. This is a map view of part of Otsego County near where I live. We shot about a 35 square mile three-dimensional seismic set in here in 2013. Some of these reefs were known reefs, and some of them are actually reefs I'll talk about later that were water flooding and CO2 flooding right now. Others were reefs that we discovered that early seismic data had not discovered, like this guy right here. And his software, which is called VizCube, is able to give a three-dimensional depiction of what all these reefs look like on this gently sloping ramp floor in Silurian time. It's really cool technology. Alan contends it makes him a genius. I argue with him about that. But he's pretty good. Resource plays, I'll talk about just a little bit. I alluded to them before. They are mostly shales. This is what the Antrim Shale, the one that had that big red splotch of gas wells in northern Michigan. This is what it looks like in outcrop. It is actually a much darker shale than that slide shows, and that's actually an imprint of some fossil early land plants there on top of that surface. The Collingwood Shale, this is an outcrop from Collingwood, Ontario, its type section, and why the Collingwood got its name. This is what is called a shale beach instead of a sand beach at a state or provincial park over on the south shore of Lake Huron in Ontario. The Sunbury Shale outcrops in Ohio. It has a lot of organic content in it as well. And the Utica Shale occurs here in Michigan, just above the Trenton. So it is 7, 8, 9,000 feet deep in most of the basin, but it's a very organically rich shale as well. And this is the guy that's producing an awful lot of gas and some oil from Ohio and Western Pennsylvania today. So resource shales require fracking. And in Michigan, what that meant specifically was the Antrim shale gas is a little bit different because it never got buried very deeply. So even though it's got a lot of organic content in it, it never got buried deeply enough to thermally crack and generate gas or oil out of it. It's a different animal entirely. Where Marty and I live in Otsego County, the Antrim shale is about 700 or 800 feet below our front yard, and with glacial till on top of that. There are bacteria that get into the subsurface and have a special niche that actually eat that organic debris, which is called kerogen, and they spit out methane as a byproduct of their very inefficient digestion, and they also spit out a little bit of carbon dioxide. And that is the crux of how this play developed in northern Michigan in the 1990s, when we were having a national natural gas crisis in this country. The federal government provided tax incentives for what were called non-conventional fuels. They got a little bit of a tax break. I think they got a percentage of their price back as a rebate, if you will, if they produced these non-conventional fuels, which costed more to capture and produce because they were being produced out of very, very low permeability rocks, specifically shales. And so we had a drilling boom in those northern Michigan counties for about a decade, late 80s to early 90s. Then we built up a surplus of natural gas. The credits went away, and the play was largely developed already anyway, so it didn't much matter. So the wells that still produce today are largely producing out of wells that were drilled with incentives in the 80s and 90s. This is a log that shows on the left the gamma ray response of the Antrim shale. And when you see the gamma ray kick to the right, as it is here, that means you have a higher degree of radioactivity. That radioactivity in this case relates to a lot of that organic debris or kerogen sitting in the rocks. And on the right is a graph showing total organic content of those same zones. There are a pair of zones in the Antrim that have high total organic content. The upper zone is a thicker one called the Lachine. It can get up to 10% plus in organic carbon content, and a thin lower zone called the Norwood, which likewise can get up in the 10 to 15% range. And so we look for these two zones as the places to capture natural gas. And how we capture that natural gas is a big part of my upcoming story on enhanced recovery. And there's what the Lachine member of the Antrim looks like in core. Very dark shales and a lot of natural fractures. You can see some of these natural fractures in the rock here. And what one tries to do in a frac of this stuff is to prop some of these natural fractures open with a sand grain or two to allow an expedite movement of gas through the rock up to the surface. That's it. And this is a stereo net on the left. This shows the direction in which those fractures orient. And you can see, think back to that big picture that I showed you in a slide a while back of all those northeast, southwest, northeast, northwest, southeast lattice work of structural trends and fractures across North America. Here's a microcosm of the same thing. The fracture trends are very diagnostic. They show up here in a Rose diagram the same way in measured fractures out of core, and they show up that way in bedding plane fracture sets over here. Those cores, or those fractures rather, occur in preferential fashion, in preferential direction, and in preferential places. So I'm looking, as would my colleagues, for areas where the fractures are more intense and where there are so-called alpha fractures, the big ones that can carry a greater degree of fluids in them. And with good detailed geologic mapping, one can pretty effectively map those. And that's kind of a slide description of what we just talked about. I'll jump through that. And I talked about fracking, and it's certainly a socio-political hotbed item right now, so I thought I'd talk a little bit more about that. The Antrim Shale is an interesting package of rocks, and it happens to sit just below several hundred feet of glacial till. Where we live in northern Michigan, we have 7, sometimes 800 or 900 feet of glacial till and bedrock right below that till. That till is our fresh water source, and that's our lifeblood here in Michigan. So the state of Michigan, regulatory body that's now called EGLE, it used to be the DEQ or the DNR, requires any oil and gas operator to define the base of the glacial drift, to drill 100 more vertical feet, and then case off that entire unconsolidated package of rocks in cemented casing. And then they must drill another 100 vertical feet before they can do any kind of frac whatsoever. And that's to make sure that the freshwater lens is not compromised, and that's critical. And we live there. We've got a well in our backyard that goes down into the till about 90 feet. So we are fully in accord with what the DNR, now EGLE, does to make sure that that part of our industry is regulated very efficiently. And most of our companies that produce gas and oil here in Michigan are state-based. So we all live here too. So we are in full accord with what the state requires us to do. It costs money, but it's money well spent, because at the end of the day, we've got to have good quality drinking water. Most of the frac fluids that we use are water and sand. The major other components, table salt, bleach, disinfectants, because there's algae in the water quite commonly. So to prevent a sludge from building up around a frac, you have an algicide that goes into the ground with your fracking fluids. And the key thing is it's all biodegradable stuff. And the Antrim is produced over the course of time, since the early 90s, maybe late 80s, 3.5 trillion cubic feet of gas. It was one of the biggest natural gas producing entities in North America for about a decade before the play began to deplete. Peak production occurred in 1998 and 99, about 0.5 trillion cubic feet in that year alone. And ever since then, the production has been declining at a pretty steady 4, 5, 6%. And probably by about 2030 or so, we'll be done. Okay, so let's move ahead and do a little bit of big thing for a few minutes before I turn it over to you folks and questions. You can get a myriad of opinions about what the energy industry is: good, bad, ugly, clean, dirty, wasteful, the bane of society, a lot of stuff like that. So what's ahead? Are we going to get out of this realm of using fossil fuels to generate the energy we need to maintain a society that can step forward? Well, ultimately, the answer is going to be yes. The pathway of how to get there from here is kind of the key thing right now. And there are steps we can take during whatever this long bridge period or settle period is going to become to make the pathway a little smarter, a little cleaner, and a little safer. And that's kind of what my career has evolved into in the last 20 or so years. And so we're going to talk a little bit about enhanced oil recovery, and I'm going to talk specifically about enhanced oil recovery using carbon dioxide. And we're going to talk about the concept of green oil. Can we produce oil that is ecologically a cogent thing to do until we get to enhanced solar technology, better wind technology, maybe tidal technology, and whatever else might be next out there? We're still kind of defining that path, which I think all of you folks can appreciate. Well, we are told that we are fully responsible for climate change because of the CO2 we produce. And I wanted to give you a little bit of perspective on that. For those at home, this is a slide that shows carbon dioxide levels basically from the beginning of the Cenozoic era, about 75 million years ago, to present. So the time scale is on our bottom axis, and on our y-axis we have parts per million of CO2. Max on the scale is 1600 up near the top. And if you'll take a look, you can see that from roughly the start of the Cenozoic until maybe roughly 30, 35 million years ago, we had atmospheric CO2 content between 500 and well in excess of 1,000 parts per million. And during that time, or during much of that time, we had both warming going on. There were hot spots on the Earth's planet. There were also periods of continental glaciation going on. So the story is not one that can be depicted and related to one atmospheric factor or any other factor alone. It's more complex than that. If we look at the right, that star is about where we are right now. We're right around 400 parts per million, of atmospheric CO2. At the beginning of the Industrial Revolution, we were probably right about there at about 300. So probably 100 parts per million of CO2 are probably our responsibility at some level. So what's that mean? Well, it means we're belching a lot of CO2 into the atmosphere. I guess that's the obvious case. The question is, are we doing everything to the climate with that 100 ppm of CO2 that some would say that we are? And that's a tough question to answer. Going back to the rocks that have been my kind of pet project for several decades in the Niagaran, atmospheric carbon dioxide levels when those reefs were being laid down was in the 8,000 to 10,000 parts per million range compared to 400 today. And we had both warm spots and cold spots there. The reefs that we are producing out of northern Michigan at the time those were laid down were sitting at about 10 degrees to 20 degrees south latitude. We were in the southern hemisphere back then. The poles rotate and flip fairly regularly over the course of geologic time. And we have the wherewithal to measure that today. And so we were sitting in the subtropics in the southern hemisphere. So maybe we'd be sitting somewhere like off the Brazilian coast today as kind of a quick comparator. And while we had that going on in Michigan, there were places on the continent where we had continental glaciation going on. We can look at Silurian age glacial tills in other parts of the world that date back to the same time. So it is possible to be both quite warm and quite cold at the same time with 20,000 ppm CO2 as it is to do so today with 400 ppm. So other things have to be brought into play, and trying to define what those other things is one of the challenges that climate scientists have today. And we enter into this equation because we are capturing CO2 and putting it back in the ground to generate new oil until we get to the point where we'll be using something else. So that's our little niche in this grand scheme of interesting questions and things to learn. Okay, here's today's quiz. Anybody got an idea on who this chap is? Handsome guy, kind of a period piece, the way he's dressed and the way he looks. We have any chemists in here? I know we have an interesting group of people from various walks of life. Nope. This is the well, or maybe not so well known, Svante Arrhenius. And Arrhenius is kind of, in some ways, you could call him the godfather of climate change theory, because that's kind of what he did. In 1896, he produced a Vanguard scientific paper that really related global warmth, or the potential of global warmth, to atmospheric CO2 levels. He was kind of the guy that Al Gore wished he were. And independent of anything else, if we just talk about CO2 content in the atmosphere alone, Arrhenius showed 130 plus years ago that there's no doubt that that has an impact on the temperature of the Earth's surface at some level. And measuring that some level is kind of the challenge that he left for those going forward. And we're still in the process of working on that. Interesting sidebar, we've talked about 300 parts per million during the Industrial Revolution, 400 parts or thereabouts today. Water vapor is also a global warming element in the atmosphere. Not quite as efficient as CO2, but water vapor typically comprises about 4 to 5% of the Earth's atmospheric gases. And so it's a part of the equation. Just a piece of food for thought there. And the unresolved key question is, okay, when you've got complex things going on in the Earth's atmosphere regarding gases, and you've also got the fact that the Earth's orbit changes over the course of time, the Earth's tilt changes over the course of time, and we have an astronomic cycle called precession, where the Earth kind of wobbles and does so on a 22,000-year cycle. All of these things collectively are doing things to climate, which we can measure kind of on a micro scale right now, and are kind of sort of getting to a place where we can measure them better and more efficiently. And right now, for those that are really serious about climate science, which means we can toss out the journalists and the politicians because they've got different agendas, there's still good science being done out there, and good science means doing your homework well, following scientific method, testing things thoroughly, vetting yourself, asking yourself if you missed something or goofed up someplace, and having your peers do the same thing, go back and take a look at your work and say, you forgot something. And that's kind of the stage we're in right now. We as humankind are having some kind of an effect by what we're doing in the atmosphere right now. We just don't know whether that some kind of effect is a catastrophic thing or a thing we can manage, a thing we can mitigate. And those are important societal questions that I think we're, for the most part, taking an intelligent look at, especially when you get down to the level of research science. I'm not so sure about the journalistic side of the political side of things. So we have a small role in all of this because thinking back to that big red splotch I showed you a few minutes ago of the Antrim Shale in Otsego, Montmorency, Kalkaska, Crawford counties, that natural gas that we produce and sell out of those shallow shale wells has a CO2 content of about 30% when those wells are fully mature. So essentially 1/3 of all that gas we produce is a waste product. And this is a CO2 removal plant that is about 3 miles as the crow flies from our house in Otsego County. And it's operated by Phillips Petroleum today. And there are several other ones in that same general vicinity that take the CO2 out. Historically, those big stacks were venting that CO2 to the atmosphere to the tune of 15, 20, 25 million cubic feet of CO2 every day, just being belched out to the atmosphere. And that sounds like a lot, and it is. And there's the 30% number once again. And these are a couple of my partners at Core Energy. That's our CEO, Bob, and his wife, by the way, Kristen, is an alumnus of this college. And that's my geophysicist partner. Oops, I did it again. Wrong punch. That's my geophysicist. I did it again. I keep missing the red button. I am trainable, just not fast. That's my partner, Alan, my geophysicist partner. He is exactly 1 day older than I am, so we tease the heck out of each other about that, and he's really good. He can be a little bit arrogant and a little bit stubborn, but he is really good, and he's fun as heck to work with. So a good geologist and a good geophysicist working on a project together is probably about the closest thing you can have to a marriage in some respects. And that means that sometimes the arguments take on the arguments you might have at home with a partner. And we bark at each other a lot, and we might even call each other names or two once in a while, and then we go drink a beer. They're good to work with. So today, actually, this is a little bit dated, but since the 1990s, we were sending as much as 1,100 kilotons per year into the atmosphere from all this Antrim gas. And cement plants belch a heck of a lot of CO2 into the air, do kind of the same thing. Most power plants do the same thing, especially those that use natural gas or coal as their primary fuel. So there are source points all across North America that are sending copious amounts of CO2 into the atmosphere. So how do we deal with that? Well, we think are a small part of that solution because we have the ability to capture CO2 at those gas plants over by our house. And we do that today, the tune of capturing about 20 million cubic feet or 1,100 tons of CO2 every day from that big plant I showed you. And we have a small plant, kind of a pony plant about a half mile away, where we clean that CO2 to 99% plus purity. We dewater it and we compress it to 1,350 pounds per square inch. And we own a small network of CO2 pipelines that go to several oil fields within 25 or 30 miles of our source point, inject it back into the ground and put it to work for us as part of enhanced recovery projects. And when we're done recovering oil, it stays in the ground. And so that is the whole concept in a nutshell of what's called CCUS, which is short for carbon capture, usage, and sequestration. This was called CCS for a lot of years by the folks in government and elsewhere. And in part through our influence and some of the testimony that our company gave to Congress, we said, okay, you're forgetting one thing. Before we put that stuff back in the ground and sequester it, what about if we use it for something of value to society and maybe get a little bit of something positive for our efforts to try and clean things up a little bit? And so we've been doing that as a company now for about 20 or so years. And so we capture 15 to 20 million cubic feet every day. We recycle the CO2 that we produce with the sludge, if you will, of oil, salt water, and CO2 that comes out of those wells every day. Separate the CO2 again, pop it back into the ground, put it to work a second, a third, a fourth time. And that's our small bit of work that we do on that. And it's kind of a simple, elegant process. Once we compress that CO2, we inject it back into an injector well in one of those reefs I showed you a while back. That CO2 mixes with salt water that's natural in association with oil and gas. And there is a zone where everything becomes perfectly miscible at high pressures. And what that means is, it doesn't mean that the CO2 chemically combines with a molecule of oil. It doesn't, but it has enough common attributes that basically it acts as a single phase of CO2 and oil. And the CO2 helps expedite moving that oil through teeny tiny pores and getting it out to a collection well and then up to the surface to produce. Along with the CO2 and water, they're reseparated and sent back to places out of harm's way. And that works at depth, and our wells are roughly a mile deep below where we live in Otsego County. That works because once you compress CO2 to the 1,350 pounds pressure that we utilize, CO2 takes on a different phase, which is called a supercritical liquid. And so it has some attributes of a liquid, some attributes of a gas. It might work a lot like if you drank fizzies as a kid. It's kind of the same thing. You've got this fizzy component that is a little bit of CO2 and a little bit of oil just kind of bubbling their way through teeny tiny pores and eventually getting to some place where one cannot collect those things. So it's kind of simple elegance that comes for a price. It's not a cheap thing to do, but it's doable. And it's doable if your CO2 source point is especially close to where you want to use it for an enhanced oil project. The reason for that is CO2 under high pressures is highly, highly corrosive. And so our pipeline is stainless steel. And so it's expensive pipeline to build and maintain. And if you've got to move CO2 hundreds of miles right now, the problem is not totally solved. So that's one of the perhaps societal problems regarding capturing CO2 that we haven't quite figured out yet. It's going to take some kind of mega project, maybe mega tax incentives, who knows what. To move CO2 long distances is still an unsolved piece of the puzzle, but we're kind of on the early phase of solving some of the smaller pieces that show kind of a meaningful pathway, if you will. And that's an aerial view of our central processing facility in northern Otsego County. All this lattice work of pipeline here goes into the ground for several miles and visits every one of the dozen enhanced oil recovery projects we have in northern Otsego County. And then all that stuff comes back to our central processing facility, separated here, the water separated out, CO2 separated out, tank batteries back here to store the oil we produce for sale, to store the salt water we have to re-inject back into the ground out of that injector well. So we, by state statute, are allowed to inject that salt water back into the ground into the Dundee Formation, which I showed you as an oil producer in central Michigan. In northern Michigan, it's not. It's all filled with salt water. So it is a dedicated and approved storage unit to send salt water back into the ground and get it out of harm's way. 50 years ago, that stuff might have been dumped on the ground if we had this technology, who knows? But anyway, we get that out of harm's way as well. The CO2 goes back into work and recycles again and again. And when we've finished our work in enhanced oil recovery, that CO2 is going to go into these reefs and be a mile deep and permanently out of harm's way. So it's kind of cool, and it's why I'm still working part-time today, because it's something I never, ever thought I'd be doing when I was looking for oil at Shell and at Tenneco 40 and 30 years ago. So it's kind of a cool thing. Maybe I'm contributing something of worth to society. I sure know it's challenging and it's fun. And I get to work with fun people that are innovative and creative. So I'm still enjoying what I get to do. As I alluded to, it's a very efficient way to enhance oil recovery. We get about 40 to 50% as much oil out of our enhanced recovery fields as the primary operator got during its earlier life. And that was quite commonly Shell, as well as a couple of other companies. But we're pretty good at this, and that doesn't mean that we come up croppers once in a while. We've drilled holes that didn't tap into the permeability conduit, and a well at 5,000 feet deep once you put infrastructure on with it. It's $1 million investment, which if things don't work out quite right, can be $1 million mistake. And as I tell my partners, it's a mistake only if we don't get smarter from it. I mean, we are in a business that is high risk and we are going to fail fairly commonly, maybe almost frequently. And if we just say, okay, we screwed up there, let's go to the next one without learning something from it, then we failed. That's a legitimate failure. But if we learn something, get a little bit smarter and maybe apply it to the next well we drill or the next reef that we flood, then we're probably doing ourselves a good thing. So that's a little bit of the whole idea of green energy. We're producing greener energy through enhanced oil recovery, but not entirely green. And I wanted to introduce you to this guy here. His name is Chuck McConnell, and very brilliant, dynamic speaker. If you get a chance to hear this guy talk, go do it. Longtime researcher in the whole field of carbon sequestration and carbon management. He was in the Obama administration as the Assistant Director of Energy back in the early teens. He then went to work as vice president at Battelle Institute in Columbus, Ohio, which is a think tank that does a lot of governmental sponsored and associated projects. And so he's dealt with the high-level politicians on the critical questions involving energy future, smart energy future, et cetera. And today he is the executive director at a think tank associated with the University of Houston that is looking at this whole broader topic of carbon management. And he's a dynamic, eloquent speaker. Well, some of his bullet points that I've taken from hearing him talk a couple of times are that we're on a far better pathway to being carbon neutral than almost anybody else on the planet, even though we're by no means perfect in that regard at this point. Most nations that have endorsed the Paris Accords really haven't gotten very far down the path yet. And sometimes they've taken backtracks and retreats because the technology isn't quite fully there yet. Germany is, for instance, just endorsed at the governmental level, building several new gas power plants that are going to belch a lot of CO2 out because they were having an energy crisis that alternate ideas were not effectively solving. And there are stories like that all over the board. And the kicker to all that is energy fuel consumption, including fossil fuel, continues to increase because a lot of what we used to call third world countries are quickly evolving out of being third world countries. I just read an article a couple of days ago about the fact that several nations in Africa are buying record amounts of coal from the United States because as they urbanize and modernize, they need electric power, which they never generated for large parts of their country. And they're building gas plants to generate power as a short-term part of their solution, but they don't have methodology in place to capture or put away the CO2. China's doing the same thing. China and India did not have to sign the Paris Accords because they were regarded as third world developing nations. That's kind of a reach. China will buy every ton of coal from the United States they can possibly buy right now. So as a broader global initiative, we're not really solving the puzzle quite yet. We're moving the puzzle forward. So it's kind of on us as a nation and as a society to do what we can to use what we have more efficiently, to find ways to capture CO2 as our company captures, to put it away efficiently and maybe do some example setting. And we've gotten some pretty good support on that, really from both sides of the aisle at the federal level, because even though those two sides of the aisle disagree on the severity of the issue of climate change and global warming, they both are in general accord that getting that stuff out of the way and putting it back in the ground is a pretty good thing to do. And they came to the conclusion after a lot of debate that instead of making it a situation where let's tax the heck out of people that put carbon dioxide in the atmosphere, should we make it punitive? No. Why do we make it incentive laden and say, if you can capture it and get it back into the ground, we'll give you a few dollars of tax credit on the energy you produce accordingly. And that helps keep us in business because to produce a barrel of oil the way we do it with enhanced recovery, our break-even point for a barrel of oil is probably somewhere in the $60 to $65 a barrel range. If the price goes below that, we lose money. And if we lose money, we don't stick around very long and I don't get a retirement. So I think we're approaching it in a pragmatic way. And this guy has some very compelling thoughts about that. And he made a comment to us at the last talk he gave. And he goes, okay, he says, raise your hands. How many of you guys are carrying one of these guys with you today? and I'll bet everybody is. Just to create one of these things, and most of them are coming out of China or elsewhere in Southeast Asia, the energy to make one of these guys, no less operated, takes the amount of energy to run 2 average-sized American homes for 1 full year. And we're kind of late to the dance in having these things in our pocket. Communist China went from basically having no means of communication, no overland telephone wires or anything else, to everybody having one of these guys. And the energy to make these guys does not come cheaply. So there is a challenge out there that maybe societally we don't all fully understand, but it's a very daunting challenge. And so it's incumbent on us to kind of do what we can to help answer that challenge. And again, to be innovative, to use the science we have, to vet it, to test it. And I think I'll leave that as my parting remarks. And I've left us maybe 8 to 10 minutes for a few questions, and I'll do my best to answer them. And nobody's fallen asleep, so I did semi-okay.
You touched on it briefly about the storage of the, old fields out there.
Yeah.
And my son is actually an engineer for consumers that works on those in that area.
Mhm.
And a lot of people, he speaks highly of Core Energy as well in the Manis family. But a lot of people don't realize, right, a few miles from Holland is Overijssel,
Right.
large wells and storage reservoirs there right in our backyard.
Right. In Allegan County, there are 3 or 4 big gas storage fields. And I think Overijssel is the biggest, but there are others as well. And they're interesting too. And I actually did a little bit of work on those about 2 decades ago, but I wouldn't say that I'm very well versed on them. But those fields are not reefy fields, but they're in the same package of rocks in the Silurian where our Niagaran reefs are in the northern lower. And the reason that those fields work as they do is on the west side of the Michigan Basin, there was a major event of salt solution in those bedded salts that I alluded to above the Niagaran Age rocks. And as those salts dissolved, there were collapse features that developed around those areas of solution that basically built little domes or pillars of that package of carbonate rocks that again were fairly well insulated by non-permeable rocks above and laterally. And they're really, really efficient fields for gas storage. There's another kind of unusual one too in kind of mid-Michigan. I talked about our glacial till a little bit. Right below the glacial till are a bunch of thin, sinuous little stringy sands, which collectively are called the stray sand, which is kind of almost a garbage catch-all term. But these little stringy sands sometimes can have extraordinary high porosity and permeability. They're tough to map unless you're drilling a well every 5 or 10 acres, but consumers and others have drilled into those stray sand fields around Clare,
Marion.
over west toward Baldwin.
Marion.
Yes. I think there's an area called, is it the 5 Lakes that is the biggest place where these gas storage fields are. Cranberry's another one, yeah. And again, a very neat little efficient story as far as gas storage is concerned. And that lattice work of pipelines we have beneath us statewide is strategically pretty important, not just to Michigan and its economy, but it's in many respects, it's a national treasure if you want to look at it that way.
Well, and I think economically, it allows us to have a lower cost of natural gas.
Absolutely.
Because,
So it's good. Thanks. Much appreciated.
Since many of our homes are powered or heated by natural gas, and they're converting a lot of the power plants from coal to natural gas. And I recall back in, I think it was the first week of February in 2020, we had a natural gas emergency in the state of Michigan. Remember, they asked everybody to back off, especially the big manufacturing companies on the east side of the state. What's the state of Michigan's position in the source of natural gas going forward? I mean, can I heat my house for another 30 years or
I think
where is that?
I think the answer is going to be yes, you'll be able to. It probably is not going to come with gas produced out of the state of Michigan, I think, to be realistic. It's probably going to come out of eastern Ohio and western Pennsylvania, out of the Marcellus Shale in Pennsylvania, maybe the Utica Shale in western PA and Ohio. And those are frac plays, to be understood. So they are part of the hot button item in some of the political conversation going on right now. But again, with regard to fracking, if you're not being dumb enough to frack along an active fault line, which has happened in a couple of occasions, somebody needs a wrist slap for that. the amount of energy you're using to put those grains of sand down into a zone with natural fractures in it and prop it with a couple of grains of, excuse me, a couple of grains of sand is pretty minuscule. And if regulations are put in place and are followed, it's not a big deal. Interestingly enough, along those lines, because Michigan has been a state where fracking has taken place, not just recently, but since the 1950s, we have a fairly copious set of regulations that guideline what we can and cannot do. And the state of Pennsylvania, when the Marcellus and Utica plays really started to evolve rapidly in the early 2000s, came to Michigan, to our then DNR DEQ, and said, okay, how do you guys regulate? How can we protect ourselves? And they really kind of piggybacked a lot of our state rules here in Michigan onto what they're doing to frack safely over there. Now, they have one additional challenge over there that we don't have. In the Antrim Shale, the fluid that we use to frack is salt water that comes out of the Dundee. And so that salt water goes right back to where it came after we're done. In the Utica and Marcellus shales, most of their fracking is done with fresh water. And so they have another issue. How do they recapture that fresh water, make it safe to use, make it potable again? And so they have to go through a lot more bells and whistles in how they frack and how they recover frack water and how a company purifies that frack water before they can go about their operational business, if you will. It's further complicated in Pennsylvania because Pennsylvania has state regulations for fracking, but also Pennsylvania has individual governance projects or project areas that evolve around water drainage basins. The Chesapeake Bay Authority has its own rules for fracking. So any body of water that drains into Chesapeake Bay and the mapped area around that have their own set of fracking rules. The Delaware River has its own authority that has at least a certain amount of legislative power. So it's a challenge for operators to work there. And I would think it's probably both fascinating and frustrating at times. It's interesting.
Question about, you talked about the gas storage or southeast of Holland. There's the ANR pipeline complex down there, and there's a consumer's compressor station down there. Is the consumer's one? Is that the storage area? Or are those just pipelines?
I think that's a pipeline with a compression station. I don't think there's any gas storage over in that immediate area.
Okay.
Yeah, the biggest gas storage reservoirs we actually have in this state are primarily over in southeast Michigan in St. Clair and Macomb counties, not too far off of Lake St. Clair, Ida Township and a few others over that way, kind of the far north suburbs of Detroit. And those are old reefs, kind of like the ones up in northern Michigan. And we have, I think, maybe a half dozen or so gas storage units in northern Michigan out of those same Niagara age reefs. A couple of them are kind of in our backyard. So it's a widespread sort of thing, but collectively, we're by a fairly significant margin the highest gas storage state in the union. So strategery can be a good thing.
One more question. Since there's so many geologists in this room, this is not an oil and gas question. What about rare materials that go into our phones? I know they've been trying to mine for those, and China has got their hands on quite a few of them. Does Michigan have a potential for any of that?
Yeah, and it's a really good question. We have a couple of things going on right now that maybe will help answer that question. And our friends Bill and Linda Harrison at McGree at Western Michigan are kind of at the forefront of this. All those layered salts that I showed you a couple of cross-sectional cartoons of and alluded to, those are several hundred feet thick, and they're not pure NaCl. They've got other stuff in them, and there are at least trace amounts of lithium in some of those bedded salts. And there are a couple of companies taking a look right now at the viability of doing some solution mining in those bedded salts, seeing if they can get out enough lithium and or other rare earths to make it worth their while, and then basically re-pump the sodium chloride back into the ground, let it re-lithify to maintain the integrity of the subsurface from a couple thousand feet down. That's part one. And part two is over in the Western UP in the Keweenaw and maybe down as far as the Marquette Mining District. There has been a lot of work done recently on the rare earth content of some of those igneous and metamorphic rocks in the Western UP. Some of those might have a future. My partner, Alan, has a son who lives in Montana who was just found and has just staked a federal claim on a large mineral deposit not too far out of Red Lodge, Montana, that has all kinds of rare earth elements in it as well. And it looks pretty good from first surmise. So, but it's an important question because right now, if we go to the phones and rare earth technology and other fields like that, including the solar power stuff we've got going on north of Big Rapids that's being run by the Chinese, we're beholden to them for a lot of that stuff because they're bringing in their own rare earth materials for that Goshen plant up in Big Rapids. And we've got someone that is at least ideologically adversarial to us, kind of controlling an awful lot of our strategic business, and that ought to raise a concern. Good question.
Yeah, I think we need to ring the closing bell. But thank you, Wayne, for all of the information. And if anybody have more questions.
Well, thanks for hanging out. It's been fun. Thanks for inviting me, and I really enjoyed my time and hope I gave you some nice cogent things to think about. I'm off the clock, right? So that thing is an on-off.